Okay, so ideal transformer is, as the name suggests, you can say that it is the lossless transformer, or you can say it is having 100% efficiency. Okay, so when we say that it is a lossless transformer, then it means that it is having no losses. So if it is having no losses, so first of all we should be in position to understand what are the losses in the transformer. So broadly we can say that there are two types of losses. One is the iron losses and other is the copper losses. Iron loss, it means that the losses which are occurring in the iron parts. Okay, and what are the copper losses? Copper losses are the losses which are occurring on the copper parts. We should know what are the iron parts. And in the previous class, I have explained you that our core or the transformer core is made up of iron parts. It can be ferromagnetic material or permanent magnetic material or any ferrous material which is having high permeability. Okay, so the transformer should not have any iron losses, and these iron losses are also called core losses. Okay, because iron parts are primarily located at core, although there are some bolt insulations. Bolts are there in which we use iron, but their size is very small, so their effect is also minimal. Okay, so the core losses, these are of two types: hysteresis loss and eddy current losses. So what are the copper losses? Where the copper is there. So where is the copper? Copper is the conducting material, isn't it? Iron is the magnetic material and copper is the conducting material. Okay, so the losses which are occurring in the conductors are the copper losses. So what happens in the conductors? Current flows. Okay, so current, whenever current is flowing, what kind of losses do we have? We have I square R losses, isn't it? So this should be 0. In the ideal transformer, it should be 0, but in the practical transformer, it should be minimum. Okay. So what should be done to reduce these? Now current is flowing in the primary side, also in the secondary side. So if the primary side current is say I1 and secondary side current is I2, okay, primary side is the resistance is R1, secondary side R2. So whatever may be the magnitude of the primary current and the secondary current, so will be its losses. Okay, so you can say this: if it is represented by Rp and Rs, then the copper losses become total losses in the transformer. Copper losses becomes I1 square Rp plus I2 square Rs. So what should be done to reduce these losses? Current will flow obviously, because whenever the load is connected, current will flow. That cannot be avoided. But the unnecessary resistances, these can be avoided. Okay, so the resistances of the primary side and the secondary side should be zero. Okay, this is what we mean by copper losses. So the copper losses is also having one more name, ohmic losses. Okay, so why it is ohmic losses? Again, we see that it is I square R losses. So one name is due to the passage of current. Passage of current is in the conductor. Conductor is copper, so copper losses. Next name is due to the resistance. Resistance is measured in ohm, so these losses are also called ohmic losses. Next is that leakage flux should be zero. There should not be any leakage flux. It means that whenever a core is there, transformer core is there, and there is a predefined path of the flux. If it is moving in the same direction as assigned, there is no problem. But if there is some leakage flux or the path followed on the primary side and the secondary side, some of the flux may be aerial. So what needs to be done to avoid this leakage flux? The limbs of the transformer should be alternatively packed with the primary and secondary winding. Okay, so where does this leakage flux comes from? This is leakage flux will we know the formula of the flux is phi is directly proportional to current. Okay, so and flux is generated in the iron parts. So if there is some irregularities, voids, etc. in the or air gaps in the core, okay, or due to the presence of some other iron parts in the transformer, these leakage flux develop. Okay, and this flux is set up by the primary winding, links completely with the secondary winding. Okay, so when there is no leakage flux, it means that the all the flux which is generated by the primary side in the primary side is linked to the secondary side. Okay, so it means that there will not be any leakage reactance. Okay, because if there is a leakage reactance, then there will be a drop due to this, and it will result in the losses. Okay, and again these leakage reactance exist both in the primary side in the secondary side. So suppose this is the leakage resist or the unwanted resistance, you can say, and this is our uh, reactance. Say on the primary side it is xp. So when the current is flowing, say primary current ip is flowing, so the loss will be ip square rp due to resistance and xp due to reactance. Okay, so ideally it should be 0. It means that there should not be any drop due to the presence of the leakage reactance. So here we have written XP and XS should be 0. It means that the all the flux is confined to the transformer core only. There is no leakage. Okay. Next is that core does not saturate. Ideally, the iron parts follow the hysteresis curve, and there should be linear relationship B is equal to mu h between the B and the H. But what happens that after a passage, as the H grows, the core saturates. So to increase the core, what we have to do, we have to increase the HL. So this HL, what is this HL? This is the MMF, and it can be increased by increasing the number of turns and the magnitude of the current. Okay, so this current is the no load current, and it is responsible for the excitation of the transformer if it goes into saturation. Okay, so it means that for the ideal transformer there should not be any leakage reactance, there should not be any reactance, and there should not be any reluctance. What is reluctance? We have discussed this as well, that reluctance is the opposing force for the flux flow. So it should be 0. Okay. So, and in the practical transformer, we require the no load current. And this no load current has two components. One is the magnetizing component, which is along the x-axis, and other is our energy loss component. Okay. So this no load current is it is denoted by I naught. It is the resultant of these two, this vector. Okay, so this is the IM magnetizing, which is responsible for excitation, and this is the component which is responsible for the makeup of the losses due to hysteresis curve and hysteresis and eddy current. So in this transformer core, when we are supplying the voltage, sinusoidal voltage, a flux is set up. Since the supply voltage is sinusoidal, Vm sin omega t, then the EMF which is developed is minus n d phi by dt. So the flux developed is phi m sin omega t sinusoidal. So we can substitute this phi m sin omega t in the formula, and phi m sin omega t becomes cos omega t omega, and it is like this. Okay, minus this. Now this cos theta, you know the cos theta is equal to sin 90 minus theta. So this cos theta is replaced by sin 90 minus theta, and also sine of minus theta is minus sin theta. Okay, so suppose that this cos theta is replaced by sine 90 minus theta if it is cos theta, but here this is negative sign. So if we are to get rid of this negative sign, so it becomes sine theta minus 90. Okay, the rest of the things remain same, that is no problem. So what we can interpret from this, that the EMF whether it is primary side or the secondary side, it is lagging the flux. Flux was sine omega t, and it is, you can say sine theta, and it is theta minus 90. So it means that the EMF is lagging the flux by 90 degrees or pi by 2 radians. Sometimes we use this for 2 marks question. Okay. And we also know that the applied voltage and the EMF produced in the primary side are in phase opposition or 180 degrees apart. So if the EMF E1 is, this is E1, it is lagging the flux by 90 degrees, and E1 and E2 are in phase, and E2 and V2 are in phase, but this E1 and V1 are out of phase. So applied voltage leads the flux by 90 degrees and EMF lags the flux by 90 degrees. Okay, clear? So EMF is directly proportional to number of turns. So we can say that E2 upon E1 is equal to N2 upon N1. Okay. So this is the diagram, phasor diagram of the ideal transformer. So in the ideal transformer, we can say that this Im is equal to 0. Okay. So it is mentioned here. Now we will focus on the practical transformer, and above was based on the no load operation when no load is connected. So when no load is connected, no current is drawn in the load end or the secondary side. Okay, but in the loaded condition, what happens? The current is drawn by the load, and where from it draws the current? It draws from the secondary side, and the secondary side draws from the energy source or the voltage source which is connected. Okay, so we can say that the secondary current I2 is equal to I load IL, or the load current. It causes the primary current I1 to flow through the primary winding, and this primary current, it was flowing due to the presence of the load, so it is the counterbalancing current. So number of turns are given to us, so N1 I1 is minus N2 I2. Okay, so this I naught is the no load current or the exciting current, Im is the magnetizing component of the current, or it is also called magnetizing current or quadrature component of the current or wattless component of the current. It is in the x-axis. Okay, so it is wattless component of the current, and IE is in the y-axis. It is called the working component of the current or active component of the current, and I have told you that it is used to compensate the loss due to the losses occurring at the core. Okay, so that is why it is also called core loss component of the current. That is why it's also called iron loss component of the current or energy loss component of the current. So these core losses, which are hysteresis and eddy current, why are they occurring? They are occurring in the core of the transformer on the electric machine. It can occur on the transformer or on the electrical machine, rotating machine as well, due to the alternating or the pulsating nature of the flux. We know that the flux is sinusoidal here, so that is why these losses are occurring. And hysteresis, it is the power spent in creating the continuous reversal in the magnetizing properties of the iron and the steel molecules in the core. Okay, so why is this loss occurring? Because in the since the core is subjected to alternating flux, so the properties of these ferrous materials or the steel, iron, it is affected. So due to this, a loss is occurring, and this loss is known as the hysteresis loss. Okay, so its formula is neta bm to the power 1.6 fv. So this is in watts. This power loss is in watt, where this neta is the Steinmetz constant and v is the volume of core in meter cube. Okay, in SI system. So we have taken SI system. So the power loss is also mentioned in the watts.